All right, let's start. Okay, so far in our grammar for symbolizing the logic that we're doing, we've kind of been using three things. We've been using sentential connectives, truth functional sentential connectives, and or not, etc. And we've been using parentheses, and then we've been using letters to represent entire sentences. And remember, in the context of this class, a sentence is basically a formula that you can assign the truth value to. He's using sentence the same way that that first book used statement. So that's all we've had so far. We've had to use just a letter to represent an entire sentence. It's not a very, what's the word I'm looking for? The opposite of coarse. Fine. Yeah, it's not a very fine-tuned way of looking at a sentence. It's a very coarse way of looking at a sentence. We're taking these big blocks, and when we were analyzing tautologies, we noticed that we were a long ways from being able to identify in specifically mathematical tautologies, right? For like just a simple math proof. So we're going to introduce three more pieces that we can use to construct these formulas and to apply logic to and learn how to work with, learn how to do proofs with. So far we've just been using these two and then sentences, using variables for sentences. Now we're going to break sentences up into these components. And that's the big part of chapter 3, is learning how to break it up like this and understanding what these three components are. So that's kind of big picture of what we're doing now. With me so far? Okay. We don't want to be so coarse. Okay, so we're going to introduce terms, predicates, and quantifiers. Now, a term you're already fairly familiar with. It's either a variable or a constant is the intuition for it. You use terms all the time in math. Predicate is the one of these three that's probably going to be the weirdest for you guys to get comfortable with. But what's a predicate? A predicate, intuitively, is stating a property of a term or stating a relationship between terms. Should probably lower that to get the glare off. And then finally, quantifiers. There's two types of quantifiers that we're going to be using. We have the universal quantifier and the existential quantifier. For those of you who've, I know we did them in discrete math for sure. We use these quantifiers. I don't know if we did in calculus. We did.
Well, like,
I don't know if we did in geometry. Yeah, there exists, and for each or for all, however you want to interpret it. Those are the two quantifiers that we have. The there exists is the existential quantifier, meaning we're saying something exists, and the for all or for each is the universal quantifier. So we're saying it's universally true for the set. Anyways, so big picture for this chapter, these are the ideas that we're covering. Okay? So first new idea. You already understand sentential connectives, you already understand parentheses, hopefully.
yeah.
So first new idea is going to be terms. So let's get into terms, and we'll take the definition head on, and then we'll look at examples, and then come back to the definition and make sure it makes sense. So a definition of a term. An expression which either names or describes some object, or results in the name or description of some object when the variables are replaced by names or descriptions. Sounds kind of weird. So let's look at an example real quick and then we'll come back to it. So
It's like an adjective.
no, it's the term, it's the subject, it's what it's about. Is what the term's going to be. So up here we have everything is red or not red. I can rewrite that as for every x, x is not red or x is red or x is not red, where x is acting as a variable there. With me so far? So x in this case is acting as a variable. Now if I were to replace x with some description, well, let's just see an example really quick. Let's look at this one. Here's a good one to help you with this, and we'll come back to it. Isaac Newton is the greatest mathematician of the last 3 centuries. Okay, so notice in this sentence, Isaac Newton, that's a particular person. That's a particular thing. We know exactly what an Isaac Newton is. That's naming one and only one thing. You with me?
Mm-hmm.
The greatest mathematician of the last 3 centuries is also naming one and only one thing. There was only one greatest mathematician of the last 3 centuries. You with me? So if we say Isaac Newton, we let A represent Isaac Newton, we let B represent the greatest mathematician of the last 3 centuries, and what this sentence is basically saying is A equals B.
Right.
Now, Isaac Newton in this case is a term. The greatest mathematician of the last 3 centuries is a term. So coming back to our definition, an expression which either names would have been Isaac Newton,
Right.
or describes the greatest mathematician of the last 3 centuries would have been the describes in this definition. So either names or describes, or looking up here. So look at this one for a second. We have a term over here and a term over here. Or results in a name or description of an object when the variables are replaced by names or descriptions. Let's think about it going from this way to this way. Let's say I had x equals y here, and those are 2 variables, right?
Right.
If I replace x with Isaac Newton, a name, and y with the greatest mathematician in the last 3 centuries, I just replaced 2 variables with a name and a description. And so those still could have been terms. So that would have been the second part of this. Or results in a name or description of an object when the variables are replaced by names or descriptions. Make sense? So variables are terms, and then constants are terms. Constants, we have 2 types. We either have names or descriptions of objects. With me on terms?
Yes.
Anything weird? Okay. And then one of the points that the author was making back
Wait,
to
what's a variable?
exactly how you think about it in math.
Represents an object.
Yeah, it's not a particular object, right?
Okay, obviously, yes. So you have your A or B, or you have your Isaac Newton.
So right here we have a bunch of variables. We don't know what numbers those are. We just know that those variables represent any number, essentially, right? So notice how if we take this sentence and we add the variables that the sentence is talking to, it turns into something like this. If I say everything is red or not red, I'm saying for every x, x is red or x is not red, which is kind of a mouthful to go from this to this. It's kind of messy. Why would we want to introduce variables into our sentences?
It's more precise.
The way the author says is, let's look at some use cases. He says, try and say this in words. No using variables.
X multiplied y plus.
No, you said x, you said y. Don't name the variables and tell me what this is stating.
Well, it is variables. What are you supposed to do?
It's saying that the product of the first number with the sum of a product of a second and third number is equal to the product of a first number with the second number and, you see what I'm saying? So we took variables to identify some things being talked about in the sentence, and we represent them. So it helps us with math all the time. You'll notice that, well, you won't notice, but one of the classes I had to do is called History of Math, and one of the things we do is we solve math problems that are really old math problems, and before the concept of a variable came to people's minds, that's how wordy math problems had to be.
So you literally took a class on word problems?
History of Math is what I took.
I know, I'm just saying. Like, everyone takes word problems as a...
Right, that's because this is so nice to deal with. When I give you this exact same information in words, your brain has to try and figure out how to interpret it this exact way. Okay. Some more examples of terms, just a bunch of examples. X plus 3, that's a term. Right? Is this a particular number?
Yes.
No.
Oh, well.
But once we replace the variables with a particular number, then this is now a particular number. That's how you identify if it's a term. Is this a term?
Yeah.
What about the fattest man of township X?
No. Yes.
Yes,
It's describing.
it's a term. Once we replace X with a township, we are now talking about a particular person. Remember what a term is. An expression which either names or describes some object, or results in the name or description of an object when we replace all the variables with names or descriptions. Make sense? That's too much noise. It's really warm in here though. Huh?
What's our township?
well, it doesn't matter. The point is, once you put in a township,
I know.
there's now only one fattest person in the township, and we know exactly who you're talking about.
No.
Okay, so that is terms. Any questions about terms before we move on to predicates? Nothing? Ready to go? Should be scrolling along in the book to make sure I don't miss any discussion that he brings up.
Aren't terms essentially nouns?
Well, not always nouns, because it could also be the description.
The fattest man. But
Yeah, but I mean,
it's
it's not like kind of.
Naming a thing rather than the name of a thing.
Yeah.
Yeah. So we went through that, x is greater than 3, that's one that I missed, but once again, x is greater than 3. Is that a term?
Not two terms?
X is greater than 3, is that a term?
yes.
Yeah.
Because once
If
I
you
replace
said
it with 5 is greater than 3, then we're talking about a particular object, right?
And it feels like you should say
No,
more like
that's what
X
he's saying.
greater than
It's
3.
two terms. There's a term x and there's a term 3. And now the greater than symbol is talking about a relationship between those
Okay,
numbers.
what about equal?
So that greater than would actually be what we call a predicate.
Oh, because.
Okay.
So in x plus 3, you give x a value, you know what that term is now.
A term has to be naming a particular object.
Right.
Once you replace the variables in there with names or descriptions, it has to be talking about a particular object. X is greater than 3, even if I replace the x with something. X is greater than 3, even if I make that 5 is greater than 3 or 1 is greater than 3. I'm still not naming a particular object. I'm talking about a relationship between two particular objects. Right? So that's a good introduction to predicates. Now the author doesn't explicitly give a definition of predicate.
Why?
I don't know. He does that a lot, and sometimes later in the book he finally gives a definition for something he's been using for a very long time. You'll notice that we're finally going to get a definition of sentence at the end of this chapter, which is a word we've been using since the beginning. No, we never defined it.
Interesting.
We just used it. So, maybe somewhere down the road he's going to finally give us a definition of predicate. He doesn't give it to us in this chapter. That I know for sure. So, intuitively, what's a predicate? It's stating the properties of, or the relationship between, terms. Okay? Notation, as a matter of notation, from here on out, I should have put a note here to say this. That was on me. We're now going to use, so just as a matter of notation, if we're talking about a name or a description, we're going to use lowercase letters at the start of the alphabet, like A and B, to represent it, or constants, the way we talk about it in math. If it's a variable, we're typically going to use letters close to the end of the alphabet, like X, Y, and Z, same way we do variables in a math class.
If it's what?
So, the same way that we're going to use the same convention that we use in math. If I'm talking about a name or a description, something that's a constant. In other words, if it's a term it's either a variable or a constant. Right? Variable, what's it talking about? It's variable. It's not talking
So
about
you're saying
singular.
variables are like X, Y, Z, constants, or A, B, C?
Yeah. So that's going to be, as a general rule, how we signify them. Same way we did in math, right?
Why is it very
That's not really the same way we did it in math, because in math we never represented constants with letters.
You did.
How many of you know the quadratic equation?
Right. I was gonna say. Okay.
So it's x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. A, b, and c in there are all constants. X is a variable.
A, B, and C are
You plug in A,
variable
B, and
stuff.
C.
Huh?
A, B, and C are variables though.
No, they're just coefficients. So if I were talking about an equation like 3x
Yeah,
squared plus 2x
That means you have to
plus
give an
1
actual example.
equals 0.
Oh, it's
In this case,
representing-
the A is representing the 3, the B is
Oh.
representing the 2, the C is representing the 1. The x is still a variable.
So is that a common convention in mathematics?
Yes, it's an absolutely common convention in mathematics.
I didn't know that.
You might be a little bit confused by it because in discrete math, that author intentionally uses the A's, B's, and C's to signify variables that are integers, and the X, Y, Z's for variables that are real numbers.
I didn't even pick up on that.
So,
I didn't have picked up on that at all because I've seen A, B, and C in a lot of other math problems that were variables, not constants.
but yes, as a general rule, the convention is we use lowercase letters at the start of the alphabet for constants, lowercase letters at the end of the alphabet for variables. We're going to follow that same convention in here. So if you were to see something along the lines of, well, and let me say the second part before I continue. And we're going to use capital letters to represent predicates. Same way we did relations in discrete math.
And they can be anywhere in the alphabet.
Yeah, there's no particular place in the alphabet. So if you come across something like this, if you see a little a, you know that this is a predicate and this is a constant. And if you see a little x, you know that this is a predicate and this is a variable. Make sense? That's just going to be the notation that we use. Okay, so let's look at an example real quick. Is red is a property that something might have, right? Something is red, James is red, I might represent, if I let R be the predicate is red, and if James has redness, I might do R applies to James, something like that.
So when you put them next to each other, it's set
The-
applies to?
Huh?
How do you say that? So you say R applies to J.
That's the way I say it. The author makes a specific note saying you still read this as X is red,
Oh, okay.
but how you want to read it, I mean, that's your own interpretation as long as you interpret it in a way that makes sense. I'm going to say applies to most likely. That's just,
Red applies to X.
yep. Redness applies to X, or not redness applies to X. So so that's taking this exact sentence. So we took this sentence, everything is red or not red. We put the variables in there. For every X, X is red or not red. Now we're going to put the predicates in there. For every, for every X, redness applies to X or not redness applies to X. With me?
Mm-hmm.
Okay. Let's look at another predicate. So we'll start out with a sentence. Every man is an animal. We're going to put in our predicates and we're going to put in our variables. So for every X, man being applying to X implies animals applies to X. If X is a man, then X is an animal. For every X, if X is a man, X is an animal. Every man is an animal.
Really?
See how this and this are saying the same thing?
Yeah.
So you remember how we would read those paragraphs and you'd have to start breaking up into its logical pieces? This is going to be the next level on that.
Right.
So you're going to be taking sentences, you're going to be breaking them up into their logical pieces, and you're also going to be identifying the variables, and you're going to be identifying the predicates that you want to talk about, and you're going to be continuing from there.
Isn't predicate a grammatical term?
It's a word. It's a word that a lot of people use. So we talk about predicates all the time in computer
Predicate
science.
nominative, that's probably
We're
why.
talking about predicate.
When you diagram this, or when you're doing
In
it,
English.
in English.
Okay. So let's continue to talk about Emma and Mr. Knightley.
Nice, we got Pete.
Yeah.
was very good.
We're picking on all of you. So we have the sentence, Emma was very gay, and we have Mr. Knightley was considerably older than Emma. Okay? So this one's pretty easy to do. The being gay predicate applies to Emma, but here's the weirder one. So we have Mr. Knightley was considerably older than Emma. Notice now that this is talking about a relationship between two terms. We have Mr. Knightley as a term, we have Emma as a term, and then we have the relationship between them was considerably older than.
Why is it K before O though?
Right. So we're saying the considerably older than predicate is operating on Mr. Knightley and Emma. Or Mr. Knightley was considerably older than Emma.
So order matters quite a bit.
Order matters. Whichever term comes first. I mean, there's some common sense interpretation of how to place it. If you know that this was considerably older than, you know that that's calling for two terms. So the first term goes in the first place you find, and the second term goes in the second place you find. Make sense?
Right.
Another thing to note about when you're identifying the predicates, you can combine them together if you want, or you can distinguish them if you want, depending on what you're trying to prove. So when I'm looking at Emma was very gay and beautiful, we can split that up into two different predicates. Or if we let W be the predicate G and B, then we're just applying one predicate to Emma.
Right.
So if you're dealing with a sentence where these two predicates seem to always be put together and there's no reason to separate them out and deal with more terms, you don't have to separate them out. So there's no requirement to do that. So this is a perfectly valid way to do it. This is a perfectly valid way to do it. Make sense? Any questions?
So how does this apply to things like tautologies?
Well, so far we've only been able to identify tautologies that were tautologies just from the sentential connectives that they used.
Right, well your first example there, everything is read or not read, seems to be a tautology.
Right, it is.
So how does that work in general with all predicates?
How does that work in general?
Well, that's one, what I'm saying is that's one specific example. Everything is read or not read. Right? So
Right.
your predicate being is read, that applies there. What about all the other predicates that exist? What's the general rule for a tautology? And like, do things change?
Well, so we kind of have a little bit of a ways to go because before you can talk about if it's a tautology, you need to determine whether or not it's true or false. And so far we're kind of stuck not knowing how to determine the truth or falsity of particular sentences. So for example, if I say x is less than 3, that's not a sentence.
Right.
What do we do with that?
You plug in X.
So it's got a predicate, it's got two terms. So we've got a ways to go before we can start reconstructing sentences. Once we start reconstructing sentences, chapter 4 is going to start, okay, now we're going to start doing the proofs like we've been doing with these types of sentences. Make sense? So yeah, we can't just do identifying predicates. We need to know how to break sentences down into these three components and identify when it is and is not a sentence, and then we'll go from there. Back to proving, which will be using tautological implications, obviously. Okay. So predicates, stating relationships or properties that the things have. So that's it for predicates. Now we'll move on to universal quantifiers. Universal quantifiers, should be following along here. Predicates, see if I missed anything. No. And then we talk about quantifiers. Okay, I didn't miss anything. Okay, so quantifiers, like we already said, there's two quantifiers. There's a universal quantifier, which we often say the for all or for each quantifier, and then the existential quantifier, which will always say there exists, is the way we'll interpret it. So the amazing thing about quantifiers, so let's look at a sentence for a second, or let's look at an expression. So look at this: x plus y equals z plus 2. Is that a sentence? Can we determine if that's true or false?
Well, it depends if you know X, Y, and Z.
Right, so that's one way that you can do it. One way that you can do it is, if we take all our variables and we replace them with constants, we can then determine if this is true or false.
Right.
Same thing with x greater than 3, right? One way that we can determine the truth or falsity of that is if we replace all the variables with constants. If I replace x with 5, this is true. If I replace x with 1, this is false. But just x is greater than 3, there's nothing that we can do with that. So one of the ways that we can take these expressions and determine the truth or falsity of them is by replacing the variables with constants. But surprisingly, another way that we can make these types of statements true or false is to add existential quantifiers on them. You with me? So let's just look at an example real quick. So x loved y. We can't determine if that's true or false, right?
Right.
But we can add existential quantifiers onto each of the variables and then determine if it's a true sentence or a false sentence.
What?
We're all.
Oh, I haven't introduced these symbols yet.
Yeah.
Sorry, I always forget about that.
Yeah, you do.
Yeah, I know, I did the same thing before. Okay, so you're going to see this symbol now, upside down A. We read that as for all x, and then you're going to see the existential quantifiers backwards E, and that's going to be there exists x.
Do you know why we use, I mean, you often say that, like, you use notation because it's tradition, but I'm wondering, is there a reason we use those? Do they represent something?
I don't know. Not for these ones. Some of them I know where they come from, some of them I don't have a clue. Neither of those, I don't have a clue. Okay, so these are the two universal quantifiers. That's how you read it, for all x, or for every x, and then this one is there exists x. So we say x loved y, can't really determine if that's true or false, but now let's look at this sentence. For every x, there exists a y such that x loved y. Now what is this saying? This is essentially saying everybody has loved somebody.
Right.
Is that?
For every x, there's been a y such that x loved y.
Well, you have to give us what x and y are, still.
People.
Yeah, in this case it would be interpreted as people because people love. So for every person, there exists another person. For every person x, there is some other person y such that x loved y. Everybody's loved somebody is another way that we could say that sentence. Make sense? And now we can determine if that's true or false. Is it true that everybody's loved somebody?
Probably not.
It's possible to determine whether or not it's true or false, though, right? X loved y, there's no way that we could ever figure out if that's true or not.
Right.
But this is true or false. We might not know which of those, but we do know that this is true or it's false, right? Either everybody has loved someone or they haven't. One of those two is true. So this is either true or false. Let's look at another one. X plus y equals z plus 2. Is that true?
No.
We don't know. But look at this sentence. There exists a y, and there exists an x, y, and z, such that x plus y equals z plus 2. This is essentially saying there are three numbers I can find, x, y, and z, such that x plus y equals z plus 2. Is that true?
Yeah.
Can I always find three integers or three numbers such that this expression is true?
Yeah.
Yeah.
Okay, let's change it. Well, if we change this to for all. For all x, for any x you pick, I can find a y and a z such that this is true.
Yes.
That's true?
Yeah.
Yes.
For all x, for all y, for any two numbers you pick, I can always find another number such that this expression is true.
Yes.
What if these two add up to an odd? Won't this always be even?
What?
I don't know. Just throw down some weird logic, maybe someone will pick it up. Okay, what about this one?
No. That is not true.
Why no?
Yes, that's true.
No, it isn't.
No, this one's definitely not true.
For any.
For all x, y, and
Oh,
z,
right.
x plus y equals z plus 2.
Right.
For
I'm still lost.
For any three numbers you pick, is it true that the sum of the first two equals the third plus 2?
Go.
Oh no.
See, go back to this one for a second.
Yeah.
Let's go back to this one for a second. What we're saying here is, for any two numbers, there's always a third number such that this is true. So for example, pick two random numbers.
2 and 5.
So 2 and 5 is 7, which is equal to 5 plus 2.
Yeah.
But if I pick any three numbers,
2, 5, 7, 3.
2, 5, 7, 3. 2 plus 5 is 7. 3 plus 2 is 5. Nope, doesn't work. So it's not true for any 3 numbers. Right?
Yeah.
And then what about this? Is this true?
Yes.
For all y, for all z,
Not
x
really.
plus y equals z plus 2?
What?
No.
But then I just solve for the x, right?
No.
No, x is still a variable in this now.
It's starting to get obvious.
There's no way that we can determine whether or not this is true or false. What about if we switch it for this? There exists an x such that for all y and z,
Yeah.
That's true, right?
Yes.
Yeah.
I can find an x such that for any 2 numbers you pick.
Oh no, that's
Yes.
not true.
No. Okay, give me the x.
Wait.
Infinity.
Wait.
What's the
No.
magic number?
No, wait.
Give you
Oh my God.
y and an x, or y and a z, and then give you the x.
The order matters here, is what I'm trying to hammer home. There does not exist an x such that for any y and z, x plus y equals z plus 2.
Wait. Why?
What is that magic x? Tell me the x.
What do you mean?
You want me to go and pick the y and the z first, and then you'll determine what the x is.
Yeah.
That's not how it works. There is an x such that for any y and z you pick, this is always true.
So
Yeah.
Before we were saying for any y
Before
and
we
z,
were saying
there
for
exists
any
an
x and y you pick, for any x and y you pick, there is a z that makes this true.
Yes.
That one's true.
Yeah.
For any x and y you pick, there is a z that makes this true.
Okay.
This is a very different thing. There exists an x so that for any y or z you pick, this is true.
Okay, can you give me an example, like a counter example, to show that it's false?
Put in on.
Pick any number x.
Pick any number x.
Yeah, pick the number x that you think it is.
Okay.
Here, let me give you an example
Now I
of
see it now.
this in a different way, where it is true. There exists an x so that for all y, x times y equals 0. What is that magic x? It's 0.
Right.
0 is the magic x that makes so that no matter what y you pick, this is true.
Yeah, that makes sense now.
Or even
But
But
you
if we
want
switch
that-
this, what about this now? If we do for all x, there exists a y that makes this true?
yes.
Yeah.
Yes, that too.
Yes.
Because y can just be 0.
Yeah.
Doesn't matter what x you pick.
Keep us on our toes, don't you?
Sure.
So if you put that there exists an x after for all z, then it would be true.
If I switch the order of these so that this comes here,
Yeah.
yeah, because, I mean, the names of the variables here don't really matter. I can call my x, y, my y, z, and my z, x. Yeah. Okay. So let's continue. What's this statement saying? For all x, x is a miser.
Miser?
What's
a miser? Someone who like hoards wealth,
That's what it sounds like.
like, what's his name, Smog? From Lord of the Rings? He'd be considered
It's not a person.
Purple dragon.
a dragon?
Object.
It's not a person.
Talking about the dragon.
Yeah.
Smog, did I get his name right?
Is it someone implying their
That's an example of a miser.
You said so.
I said something. I sure hope so. I've been talking for a while.
Nice.
Hate to talk this much and say nothing. All right. So this is saying basically everyone is a miser, right?
Yeah.
Which is a false statement.
How is it saying that?
But you
For all
psychologist,
x.
yeah.
For all x, x is a miser. For
X is a
every
person.
person, that person is a miser.
Oh, that's
For all.
And then if I switch this to
There exists.
there exists, that's saying there's someone out there who's a miser.
that. Yeah, that's.
So that one's true, but
Peter.
the for all is false. Not everyone's a miser, but there is a miser out there.
Not necessarily. That's not what that says.
Not necessarily, but based off of your intuition, those statements would be true and false, respectively.
Yeah.
Or false and true, respectively.
Psychologists might argue everyone's a miser.
And then, here's another one that we were talking about. X is greater than 0. That's not a statement in and of itself, but there exists an X such that x is greater than 0. Now that one's true. But if I say for all x,
No.
x is greater than 0.
Assuming x
For all
is
x in
no
the
longer-
natural numbers?
See, we're starting to have a bit of a wait a second moment.
Yeah.
So one of the things that you're noticing as we're going through this, we don't know what our domain is. So for those of you who are wondering, depends on the domain, you're jumping the gun to chapter 4. We're
is
not going
that
to talk
the right
about
word?
domains yet. So for now, we're just inferring from context what's meant
Can you
and
define
doing our best guess.
domain in this context?
The set of objects that we're operating on.
Okay.
But we'll get to that. So we haven't talked about domain yet, so those of you wondering, depends on the domain, you see where we're headed.
Mhm.
Those of you who don't know what we're talking about, as long as it still makes sense to you, you're good. We'll get to the domain later. So, are all numbers greater than 0? No. So this one would be false. Okay. So, getting used to existential quantifiers. These are the weird ones. I don't know how to make them make more sense
Predicates are weird.
More
modifiers.
examples would be nice.
to you because
I guess
you
maybe.
took discrete
But
math.
it didn't seem like it was that hard to
Yeah,
touch on then.
I don't know. Seems like they always get stuck on, especially when we start negating these things. So let's negate one.
Wait, we gotta do all men and animals first.
That's what we're gonna do. Yeah. Oh. Yeah, I have 3. I only read 2. Okay. So now using our predicates, our variables, and our existential quantifiers, we're gonna start interpreting sentences. All men are animals. What are we saying? For every x, if x is a man, then x is an animal. All men are animals. Here's how we're gonna symbolize that now. Make sense?
Mm-hmm.
Yeah.
What if I were to change this to some?
Then yeah,
There exists.
you need a quantifier for that.
But doesn't there exist just only mean one? So
Some.
aren't we still missing it? This is saying some men are animals. This is just saying there exists a man such that there exists an x such that if x is a man, x is an animal.
Well, there
No.
exists does not mean
You would
one.
have to say it like this then, wouldn't you? You'd have to say for all x or
I mean, this one's kind of weird. This one's saying let's put it back how we had it before.
There exists
All
X
men
is-
are animals. This is saying
every.
for everything, if it's a man, it's an animal.
So what's x? Is x just any object?
Yeah.
Okay.
So for anything, if it's a man, then it's an animal,
Right.
right? So when we try to do some men are animals, what's that saying? It's saying there exists something such that if it's a man, it's an animal.
Right.
What about this marker? If it's a man, it's an animal,
Yeah.
But
but it's not telling me that
True. Well.
there's something that is a
false
man
implies
and an
anything
animal.
is true.
Indicates
Still
that
would
it's
be
a man,
true,
right?
So you're seeing. Well. Yeah. You
We're
have
not determining whether it's true or false. We're wondering,
Oh.
is this symbolizing this sentence? How do we symbolize
Right.
this? Some men are
There is
animals.
something-
So what I'm thinking is you
There
could
you
go for all x or every x.
There exists
I mean, there
x
exists x.
such that x is a man and x is an animal.
Hmm?
Wow. Implies X is an animal.
Can you go over that again?
Some men are animals. What does that mean? It means there exists something out there that's a man and an animal.
Oh,
right?
Oh, all men. Okay, yeah. That does.
Some men are animals. Here's the symbolization.
So why
There
does
exists something out there that's a man and an animal.
Why
Some
does it
men
not
are
work?
animals.
Why doesn't the first one work?
This one is saying there exists something out there such that if it's a man, then it's an animal.
Yeah.
That could be talking about this marker.
Yeah.
This statement is not saying if you have a marker, then if it's a man, it's an animal. It's not saying for any object out there, if it's a man, then it's an animal.
Saying you have to have a man for it to be an animal.
I mean, that's still a
It
true
says
statement.
the same. Well, it's
Yeah, we're not
Is
deciding
that not
whether
the
it's
same
true.
if there.
So,
Yeah, it makes way more
let's
sense.
let's
And
do
it's
it
like
If
this way.
something is a man, then it's an animal.
So let's say some rocks are animals.
Okay.
Notice that we would say this statement is false. Some rocks are animals, we would say this is false,
Okay.
right? Using our intuition.
Yeah.
So let's symbolize it now. Let's see which one of these symbolizations makes more sense.
There exists.
Some rocks are animals. Is that saying that there exists something such that if it's a rock, then it's an animal?
Okay.
Sure, this marker. If it's a rock, then it's an animal. Is it a rock?
No.
False. Is it an animal? False. False implies false. True.
Yeah, I know.
Yeah, so this is now true.
But we're not caring about. We don't care about the truth value right here. We're seeing if it's a valid way to represent it.
Well, we're trying to appeal to the intuition. Which one of these should be the symbolization? So think about the truth of what you know. Think about this as a statement that we know to be true.
Okay.
So we know that this is true, so our symbolization better be true. Or sorry, we know that this is false, so our symbolization better be false. Right? Some rocks are animals. No, that's not true. No rocks are animals. This says there exists something such that it's a rock and an animal is false.
Right.
Just like some rocks are animals is false.
Right.
This is saying there exists something such that if it were a rock, then it would be an animal. Sure.
Which is true all the time.
Me. If I were a rock, I'd be an animal.
You are
Well, I'm also an animal then.
Scheduling young
So does it make sense that this is a symbolization and not this?
Yeah, it does now. Because it's a little more accurate, but only a little bit.
way more.
Way more
Yes, the implication is.
represents almost the same idea.
Now, I think we'll be able to make more intuition with this once we do the negation. So let's go through the next two statements. All freshmen are intelligent. How do we symbolize this?
There exists
Big
X.
There exists X.
No. it's
No,
for
X.
all X,
Yeah. For all of X.
We're being torn. Come to consensus. There exists or for all?
It's
For all.
Okay, there exists. For all X what?
F
X
X implies
No.
IX.
Yeah.
Yeah.
Wonderful. For all X, if X is a freshman, X is intelligent. All freshmen are intelligent.
So
Wonderful.
for the universal
Now
quantifier,
the
that always-
negation. How are we going to negate this thing? Not all freshmen are intelligent.
You're saying
There
that
exists
you-
It's
the
the
same
exact
just
same
the-
thing,
Yeah,
just
no,
with
with the
Oh,
not
yeah.
at the front.
Oh, there exists.
There exists a freshman that is
Right,
not
there exists a
intelligent.
freshman that is not intelligent.
So there exists
There exists
X.
Oh,
F
such
X,
that
Such that.
does not
that's
imply.
right. It
and-
can't be all.
not IX.
perfect.
Yeah.
He was reading it
Students
out.
take
How did
longer
you
to
that?
do
I
that.
didn't read that.
That was smart.
Now, if you would have just looked down here, you probably would have gotten it. Or
Oh.
down here.
Yeah,
But that was perfect. That's exactly how you do it. So the negation of for all X, f of X implies Ix, is there exists X such that f of X and not I of X. So now let's make sense of this with a rule. So here's the rule. The rule is if you're doing the negation of for all X, some statement about X,
It's
Okay.
there exists that.
it's there exists something that's not that statement about X. If we're saying it's not true that for every X, S of X, then we're saying there exists an X such that not S of X.
Yeah, that makes sense.
That make sense? Okay. So now let's see it with this exact example that we were doing. So we said not for every X, A applying to X implied, you notice how I'm doing the exact same structure?
Yeah.
I'm just doing AX, BX now. Okay. So let's say that we have for all X, if A applies to X, B applies to X, right? And we're taking the negation of that. We're saying that's not true. Using this rule, that's the same thing as there exists an X such that this is not true.
Right.
Now notice I did a jump here. Another way that we can interpret A implies B is not A or B,
Yeah.
right?
So why do you?
So here's the implication, and then I
same thing.
move the negation inside, switching the for all to there exists,
Right.
right? Now we're going to use what rule?
Distributive property.
No.
De Morgan's laws?
De Morgan's. We're going to use De Morgan's to distribute the not through there. Remember, when you distribute the not, you negate both the terms and you switch the or to an and. So it switches it to that.
Proof.
So the negation of this gave us this.
Which is exactly what we just did.
Good?
Yep.
And then when you say it in words, it might make sense as well. If we say it is not true that for all x, if A applies to x and B applies to x, if that's not true, then that's the same thing as saying there exists an x such that A applies to x, but B does not apply to x. Right? Connecting the intuition with the actual argument. Okay, perfect. So let's continue with some.
Quantifiers.
No, this time we're going to throw in. Now we're just going to do some statements. Let's symbolize some statements. Adam is not married to anyone.
You have Adams.
Adams. Okay, it's the last name. Adams is not married to anyone. How do we symbolize this?
There exists some. What's the kind of statement?
There exists x such that
Adams.
Adams.
The person
so
with
it'd
the
be,
last name.
It'd be
There exists x such that.
not a.
No, it's A.
If it was Adams is married,
Oh,
then it'd be not.
It's
a.
not an A.
It's not an A.
What?
We didn't even use x in there.
X is your Adams.
There exists Adam. We already know there exists Adam. Adam's Adam.
If there exists a person such that Adams is married.
Remember that your existential quantifiers only apply to variables. Maybe I should say that. We already know Adam exists.
Oh.
It's our variables that may or may not exist. There may or may not be a number that satisfies x greater than 0. Right?
Okay, then isn't it just like the one I did? There exists X such that
There exists x such that.
AX, meaning the person Adam, or the person with the last name.
Married
Adams
applies to Adam and x.
No.
No.
No, Adams
There is
is
a
married to.
person
It's
that
Predicate.
Adams is not married to.
Yes. Well, no, that's not right. It'd be
That looks
every,
right.
so you change it so
What?
I said that looks right.
Well, it's almost right.
it's with the universe
For
modifier.
all x.
For all people,
For all people,
Adam
Adam is not married to that person.
but
For
get rid
all
of the A.
people.
Get rid of the little A. Right?
Is it
No.
alright?
And is a predicate.
Okay.
Is married to. A is Adams. X is person. For all people,
Anyone.
Okay.
That's where you're getting
Adams
for all.
is not
Yeah.
married to that person. For any person, for each person, Adams is not married to that person.
Yeah.
Make sense?
Because
Yeah.
Adams is
Some
just not
freshman
married.
date, Elizabeth. What are these?
All right. Now let's do some freshman date Elizabeth.
There
What is it?
exists
There
X
exists.
such that
There's
E
this Y,
X, basically, or Y.
such that what?
EY.
F Y
EY,
F Y.
No, capital EY.
capital EY. What's the
Elizabeth.
predicate E?
Date Elizabeth.
Oh, let's make Elizabeth.
Okay,
a
so yeah,
proper
so
name.
you could go Y.
Dates.
YE.
F E.
Dates FE.
No, dates E.
No,
And-
dates EY.
Y.
No.
There exists a Y such that Elizabeth dates a Y,
No, Y dates
Yes.
in Elizabeth.
but we
No,
needed a
that makes
freshman.
sense.
Okay, we can switch them. You go DYE.
Then
It
how
does
come
that
you
same
don't
thing.
make two terms?
Well, hold on. This is saying there exists a person that dates Elizabeth, sure.
Yeah.
We need a
But we
freshman.
need a freshman.
Okay, so this Y.
Okay,
What
Y
if
is a
she's
freshman.
dating
There
a
exists
top-
F
Date.
Oh,
Y.
so
There you
So
go.
Y represents a person, not a freshman.
Huh?
Wouldn't you just do like FY and DEY?
And
Yeah.
I tried.
Well, you were all talking at once.
Mhm.
There
I just
exists a
looked over
person such that Elizabeth dates that person, and that person's a freshman.
I would
That
see the
works.
freshman.
I was
coming
thinking
first.
of it as Y
Sure.
is a freshman.
We could do FY and. Doesn't
Same
matter
thing.
what order you and in.
Oh,
It's the exact same information. Make sense?
Yeah.
So these are kind of weird to do at first, but this is what you're gonna have to start doing now. You're gonna have to start taking sentences and
That's
breaking
all.
them down like this.
It's a little weird.
Yeah, we'll do a nice convoluted example at the end to help
Maybe.
cement it all in.
Or make it fall apart.
But before we do that, we need to have one more discussion, and then we'll go back to do more examples. And the last thing we need to talk about is, okay, we now know how to do all these things. We just need to know how to talk about whether or not we can assign a truth value to a particular formula. And we need to talk about what a formula is. So first, let's have the... let me scroll this to make sure I'm not missing anything. We did that, we talked about that, talked about that, talked about that.
Is that page 69?
Adam is not married. Note about what the author does. So, you'll notice when I do a universal quantifier, I do for all x. The author just does the x by itself in parentheses. So here's his for all x, and here's his there exists. So he does the there exists the same way. For some reason, he just does x by itself.
Does he ever use
For
the
all
upside down
x.
way?
Not that I've seen.
Okay.
Stupid.
Second, you'll notice he put the negation outside the parentheses. That makes 0 sense to me.
Because, yeah. When you put it right in front of the M.
Yeah, that's what I did.
Yeah.
That's this.
Because the m's a predicate, right?
Yeah.
And it's
Yeah,
not the
If you do
predicate,
that, it seems like you're nodding
It's
A
negating
and X as well.
the predicate.
Kind of.
Yeah, as long as you understand how to interpret it. Yeah, I don't understand putting the negation out here instead of inside of there. The same way that when you see he does it as and, he puts it inside of there. It's potential connections, it seems to me, should be inside of there. Because the way I always interpret going from the end of our quantifier to the beginning of our formula is such that.
Yeah, how do you represent such that?
You don't. It's the way that you read the going from the quantifier to
It's tricky.
the formula. So for all, well, we usually use a such that with the there exists. There exists x such that x is a freshman and x is not intelligent. Is how I read that. We don't really fill in with for all actually. For all x, Adam is not married to x. So I guess it's only with the there exists that I do that. Anyways, so here's his representation of those exact two sentences that we did. You'll notice it's almost identical to ours. We just use better notation because I'm cool like that.
That's right. That's right.
Okay,
Get off my turf.
moving on. Bound and free variables.
Only free.
Okay, so you'll notice that the existential quantifiers only make sense in reference to variable, right? I don't say, there exists a person such that Adam is married to Betsy. No, Adam and Betsy are already people. We didn't have a variable there. That doesn't make sense. There exists some person X such that Adam is married to Betsy. No, that doesn't make sense.
Right. Yeah.
There exists some person X such that Adam is married to X. Okay, now that makes sense. So we use these existential quantifiers in tandem with variables, not constants. So bound and free variables, in short, is going to be they're bound if they're associated with existential quantifiers. They're free if they're not.
Right. Wouldn't that just be a constant though?
No. So here's a free one. X is greater than 3. That's a free variable. We didn't bound it.
But wouldn't that
A bound one would be there exists X. X is greater than 3. Okay, now X is bound.
Right.
Not bound, or in other words, free, bound. And even if I make this a for all, it's still bound.
Why?
Because a quantifier applies to it. And that's what it means to be bound. This isn't bound like in calculus when we said
Yeah.
it can't get higher than a certain number.
I understand that. I'm just
It's
When you
bound
read
meaning
X-
a quantifier applies to it.
when you read x is greater than 3, it feels like implied for all x. So it feels like that quantifier.
That's
is already-
because in math,
you are talking about for all x.
yeah, there's a lot of contextual stuff that you understand based off the context where you find it,
Mm-hmm.
what's being talked about. But notice if I say x greater than 3, true or false? You can't.
Okay.
If I say for every x, x is greater than 3, true or false?
False.
What about if I switch to there exists?
That's
There exists an x such that x is greater than 3, true or false?
okay.
So when it's bound, you can start talking about the truth or falsity of it. When it's free, you can't.
Okay.
Okay?
Yeah.
So those were just examples. We need to build up an idea of formula real quick, and then we'll go back and talk about
I feel teams.
bound and free variables. Okay, so
Like little pins.
first we need to talk about an atomic formula. An atomic formula is a predicate followed by or flanked by the appropriate number of terms.
Flank.
Flanked means they're on both sides. So I don't know if we use relations in calculus, but in discrete math we use relations all the time, and we would do something like x is related to y for a relation. So I could use a predicate like this. This is where it's flanked, and I could have also done it like this.
Is that a K?
That's an R.
So,
I was just trying to random letter for relation.
so in those examples, you could have done instead of MAX, you could have done AMX.
Yeah, would have been
That
perfectly
makes more
valid to
sense
do
to
it.
me. It's a little more specific.
We might be saving, I don't know where the author's going to go with it, but I wouldn't be surprised if he saves using it in the middle for relations in the mathematical sense of the word. Actually talk about set of ordered pairs.
Okay.
I don't know. We'll see. Anyways, so a predicate followed by or flanked by the appropriate number of terms. Notice the marriage predicate needed 2 terms, whereas the freshman predicate only needed 1 term.
Right.
So here's a formula. Here's an atomic formula. Here's an atomic formula. What about not MAX? Is that an atomic formula?
I think it's still flank.
Yes. No.
No, it is
No.
not an atomic formula because it has a sentential connective on there. An atomic formula is just a predicate followed by or flanked by the appropriate number of terms.
Okay, yeah, that makes sense. So just a relation.
Followed.
Not
by-
necessarily a relation.
Well, a relation
Is read is a predicate.
So are relations atomic formulas? Like if you were to,
If they have the appropriate number of terms.
what's the appropriate number of terms for a relation? Well,
Typically 2.
depends on- yeah.
That's a weird definition because when you look at it, it's R X Y, and it's saying followed. How
So-
can it spell X Y R? Because your R is your predicate, and it's saying followed by.
Yeah, so look, hit the predicate
when you're
married.
writing, then it's followed.
Married followed by atoms and X. Okay.
I'm thinking followed.
There is a formula. Right? X plus 3 equals 2. Is there a formula?
Yes.
Is that an atomic formula?
No.
No. Well, you could rewrite it.
Is 3 or? Three
What's
should be
X?
You don't know.
The number such.
It's a variable.
Is it?
Okay.
Is it plus?
3 is a
constant.
constant. X plus 3, is that a term?
Yes.
Yeah, that's a term. Is
Well-
2 a term?
Assuming X is a number.
Is equals a relation?
Yes.
Oh, equals is your predicate.
Yeah, there's your predicate with 2 terms.
But it's
On
not
the
the
other side.
right syntax.
What do you mean not the right syntax?
And that,
Equals is a
can
predicate,
you, does that represent,
flanked
my point is,
by the number of terms you expect it to have. 2 equals has 2 terms, one on the left, one on the right.
but that's not how we would write it if we were answering. the
What's
question.
not atomic about
Like your first part also has a relationship in it.
it? No, that's not a relation.
That's a number.
That's an operation.
Okay.
X plus 3 is just another way of representing the number.
It's true, but what I was saying
This is just a term.
That's not how you would represent it.
This is just a term. That's just a relation or a predicate. So you have a predicate flanked by the appropriate number of terms. Let me give you an example of something that's not a predicate or not a formula.
Wow.
Okay, what's that? That's a whole bunch of nonsense is what that is.
Fix your marker. What was yours next?
Oh. I'll erase that.
That's not.
That formula? Is that
Nothingness
an atomic formula?
less than 3 is
What
not
about
equal to
this?
X.
It's not even a formula. That's a formula.
Less than 3, is that a formula?
No, that's not even.
No. It's not a formula, it's not an atomic formula. Okay. So atomic formulas. The predicate, flanked or followed by the appropriate number of terms, however many terms that predicate's expecting. Make sense?
Yeah.
Atomic formula? Okay. So now, let's get into a formula in general. These are your rules for how you can construct a formula. If you're able to follow these rules, whatever it produces is a formula. So starting, every atomic formula is a formula.
Crazy.
Next rule, if S is a formula, not S is a formula.
Oh, nice.
If S and R are formulas, so is S and R, S or R, S implies R, and S if and only if R. Make sense?
Can you give an example of that? Oh,
Can you give us a
can't.
counterexample
You
of
have to
that?
give the other term first.
I can give you an example of that,
Well,
sure.
we still don't know
So
what
far,
formula it is.
give me an atomic formula.
X plus 3 equals 5.
X plus 3 equals 5. Okay, apply the not. X plus 3 does not equal 5. And X plus 3 equals 5. Using this next one. That's a formula.
Can you define the formula for me, please?
That's what we're defining. We're doing what's called a recursive definition.
I don't like those.
So A, basically
How
you
is
start
the
out.
same thing as logically follows, and I'm like, why would they do it this way?
You start out with an atomic formula, which you understand. And now you can apply these rules to it over and over again recursively to build formulas out of atomic formulas. So atomic formulas are your building blocks. You can and them together, you can or them together, you can not them, you can use them to imply each other, logically imply each other, and then you can add existential quantifiers onto them.
Right.
So if R is a formula and X is any variable, then for all X R, where R is a formula, and there exists X such that R, those are also formulas.
Wouldn't it be Rx? Not just R?
No, I don't think it has to be Rx. Remember that our formulas aren't necessarily true. We're just saying what is a formula.
Right. Well, what I'm saying is, there exists X such that R. That doesn't make sense. Why would
Right,
we
we're not
introduce
necessarily
X?
saying that these things make sense. Let's see where our rules are. Oh, he used V. I didn't want to use V because it looks too much like or. So we're not saying that the formula always makes sense. We're not saying that you can always assign a truth or false value to it. We're just saying it's a formula.
So formulas aren't sentences.
A sentence is a special type of formula.
So
In short, a sentence is a formula that you can determine is true or false.
right. So even nonsense and gibberish is formula, or can be a formula. Is that accurate?
We could get weird things. So I could, for example, this is a formula, even though it's kind of weird.
X.
There exists X such that married applies to A and Y, even though the X didn't happen to be used.
That doesn't even, why would that even, why?
It's still just a formula. Right?
Maybe X is on an Earth.
I mean, maybe you continue with this and somehow make use of the X, maybe not.